like quantifies over the set?
I'm not sure.
With this camera, yes, I recorded my talk with another camera, and the video is on my personal YouTube account.
Yes, there do exist data types with negative occurrences which are fine. There also exists data types with negative occurrences which are not fine, which is why ACTA doesn't allow
Is it
it.
recording right now, or?
I guess.
Okay. That doesn't mean you all have to stop talking about dependent types.
And it's just a syntactic bet, and it's basically the same thing as like
the skeleton crew?
the whole thing problem.
It's raining.
Things that you can type is always a conservative approximation.
It's
So-
cold, yeah.
So Dan told me that his back is hurting him and he may not be here.
Yeah, Dan's having a problem. Amr was here earlier, but I don't know what he vanished to. And, I don't know, like Andy's out of town.
Is this projector in here permanently now?
I don't know, it was sitting here when I walked in, so.
That's convenient.
There's probably the pseudo-permanent solution. I wouldn't be surprised if it's supposed to be mounted up there, even. They just haven't.
Alright, well I guess I'll go ahead. Am I visible on camera right now if I stand here?
No, well, yes.
I am?
Yes, the LCD just sucks, so I can see. You look like a silhouette, but yes.
Oh, alright. Okay, I guess I'll get started then. So, thanks for coming. I'm going to be talking about work that Ryan and I have been working on for the past a little over a year. And for those of you who were here in March, this is going to be a much more polished version of the talk I gave then, featuring actual slides this time. And it's also going to be almost an exact retread of a talk I gave last month at Aarhus University right after ICFP in Denmark. So with that, let's get started. So I want to start by showing this tiny example program written in a hypothetical programming language. And in this hypothetical language, we have ordinary Latin expressions, of course, and we have memory locations, and we have put and get operations for writing, or reading from and writing to those locations. And then, perhaps most excitingly, we have this let par form for evaluation of multiple subexpressions in parallel. And this is doing what's known as fork-join parallelism, because while these subexpressions can run in any order, they all have to run before we get to the body of the let par expression, which is this V down here, which is a synchronization point. So what's going on with this particular program? Well, we've got a location L that we're putting the number 3 in, and then we have these two sub-expressions, get L and put 4 in L, that are running in parallel. And the underscore here, or there's no underscore, never mind. What's going on here is that these two sub-expressions are running in parallel. So my question for you is, what's V?
A letter.
Thank you. Yeah. So what does this program evaluate to? Well, the answer is it depends.
Is this like the Schrodinger's cat question?
So depending on whether the get or the put runs first, the value of V could be either 3 or 4. So this is a non-deterministic program producing different results depending on the whims of the scheduler. So this is supposed to be a talk about deterministic computation, so we're going to fix this busted program. So let's define what we do want. So I'm going to define deterministic this way. We'll say that a deterministic program is one that always produces the same observable result on multiple runs. And this is what we're talking about here is what's known as, I guess, external determinism, in that we don't care if the reduction sequence is always the same, but we care about the observable result. And furthermore, a deterministic by construction programming model is one that will only let deterministic programs be written. And a couple of examples of deterministic by construction models that we're going to revisit in a bit are comp process networks, the Intel concurrent collection system, and the Monad par-Haskell library, which you're familiar with from various people here working on it. So does anyone have a problem with these definitions as stated? So I see at least one problem, which is that there are a lot of different ways to define observable results. And what we're doing here is defining observable result to be just the value that the program evaluates to. And so that assumes that there are a lot of things we can't observe. We can't observe the heat generated by the processor that runs the program, for instance. There are settings where you might want to be able to observe that. And as I mentioned, we can't observe the choices that the scheduler is making. We can't observe the order of the reduction sequence. But it's only if those choices leak through to what we can observe, which in this case, in our example, is the value of v at the end of the program, that we get non-determinism as we've defined it.
So, is there a notion of error in the system or something like that? Could you do something that might be illegal given some ordering, but legal given another? Or you're assuming that everything is kind of nice and pure and you don't have to worry about that? Or divergence for the same example.
So if you had a program that diverged sometimes and didn't diverge at other times, then that would count as non-deterministic in this setting, yes, because sometimes you'd be getting a value and other times you wouldn't. Okay, so returning to this example program, we want to see if we can fix this, and the kinds of fixes we're interested in are not just fixes that fix this program, but fixes that fix the programming model. So they will disallow any non-deterministic program from being written. So what could we do to make this thing behave deterministically? So one thing we could do, of course, is serialize it. And this would work, but we're going to assume that it's not an option for us. That's cheating. So what else? Well, one thing that we can do, and this is an approach that's near and dear to the heart of many distributed systems people, is consider the source of the non-determinism here and observe that really the problem is that we have shared mutable state between two separate computations here. And therefore, what we can do is just reject this program outright as a program you're not allowed to write in our language. And this is what some might say is a drastic approach, but it's actually an approach that I'm fond of. And in fact, when I'm not working on this, I sometimes am working on the Rust programming language, which takes this no shared state between tasks approach. But as you might have guessed from the fact that there's a question mark at the top of this slide, and from the fact that we have shared state in the title of the talk, we're not going to let ourselves get away with this either. We're going to assume that we have a setting of shared state. But, however, I would like to suggest to you that this no shared state between tasks idea is maybe not so quite drastically different from what we're doing after all. And in a little while, we're going to look at Conn process networks, which are a model of computation that enforce exactly this property. And we're going to take inspiration from that. So I'll come back to that in a little bit. So we want to keep the parallelism and we want to keep the shared state. What can we do? Well, one thing we can do is require that variables can only be assigned to once. And that gives us a so-called single assignment model. And if we do that, and we're either going to enforce this single assignment condition at compile time, let's say with a substructural type system of some kind, or enforcing it with runtime check, then, because we tried to write to L twice here, then this program would either be rejected by the compiler as something we're not allowed to express, or it would just raise a runtime error, and therefore it would be deterministic, because programs that never run always run the same way. So this disallowing multiple assignment thing is it's a standard technique in this setting, and it's not at all a new idea. It's been around at least since 1968, when Tesler and Ania introduced this single assignment language called Compel, which is short for compute parallel. And I found out as I was getting ready for this talk, this is actually the same Larry Tesler who's perhaps better known for numerous HCI contributions, including his work at Xerox PARC, where he was one of the people who invented cut, copy, paste. So single assignment has been around at least as long as the cut, copy, paste metaphor has been around. And then in the 80s, there was some work on I structures, which are arrays, each of which components can be written no more than once. So, and that grew out of work on the id programming language. And I mentioned Ivars for the first time here. So an Ivar is just an I structure with one cell. So it's a short name for a single assignment variable. So whenever I say Ivar for the rest of the talk, that's single assignment variable is what I mean. And single assignment is still very much in use. So I mentioned a couple of brief examples, the Intel Concurrent Collection System, or CNC for short. I'm not exactly sure why it's called CNC. It was an Intel marketing idea. But CNC is, it's, I guess, somewhere in the fuzzy space between a library and an embedded DSL. And what it lets you do is, and correct me if I'm wrong, Ryan, but I think what it lets you do is write programs as collections of individual sequential subprograms and then provide a framework that composes those into deterministic parallel programs. But the CNC paper defines its semantics in terms of this smaller language called featherweight CNC. And featherweight CNC enforces determinism with Ivars. And then finally, the monad parse system. And this is work that came out by Ryan and colleagues last year at the Haskell Symposium. And then there's a second paper about it at ICFP. last month. And under the hood, it uses Ivars as well.
Okay, I've got a
Yeah.
question. I've always been curious, like, so what exactly is the difference between an I structure and an Ivar? Because in my mind, I've got this model of like logic variables, and
Mhm.
you know, they're sort of single assignment, but they have the property that you can take a logic variable and you can partially ground it to like a pair of logic variables, right? Can you do the same thing with Ivars, or is that what
Well,
an I structure is?
You can just think of an I structure as an array of Ivars.
Okay, so can you make an Ivar then? Can you assign it to be an I structure that contains other Ivars? Can you kind of push it down like a tree structure?
I think what you're getting at is something that I'm going to get to in a little
Okay.
bit. Okay, so using Ivars works, and it gives us a deterministic by construction parallel programming model, even with shared state, just like we wanted. And so this is going to be our starting point, but I'm still not satisfied. And why am I not satisfied? Well, just on the face of it, the single assignment thing seems just a little bit too heavy-handed and inflexible, and it rules out a lot of programs that we'd like to allow. So just kind of as the most basic, simple example, here's a perfectly good deterministic program that single assignment forbids, and it's one where we're writing the same value twice to L. And, well, the value of V is always going to end up being 3, clearly, but this would be ruled out by the single assignment restriction. So at a bare minimum, it seems like it would be nice to allow at least this program and allow multiple writes at the same value. And so that doesn't seem like it should be too hard, but it seems like it should be like at least within the spirit of the original single assignment restriction. But think about what I just said, multiple writes of the same value. So to do that, we have to answer this tricky question, what does the word same really mean? So we'd have to figure out what we mean by same. We need to define an equivalence relation on values. And so chewing on that for a moment, let me show you one other program that single assignment forbids. So in this case, L contains a pair. And we're writing to L twice, and each write is filling in a different half of the pair. And the bottom symbol here just indicates that we don't know and don't care about the second half of the pair on that first line. And we're not going to mess with it. We're just going to write the first half to be 4. And then similarly here, we're just going to write the second half of the pair to be 3, and we don't care about the first half. So this program is deterministic too, right? Because both of these have to run before the synchronization point, and this pair is always going to end up as 4, 3. But this is forbidden also. So these are a couple of situations in which Ivars aren't going to be good enough. And to be entirely fair, and this may have been what Will was getting at, we could fake this kind of program with Ivars. We could have a pair where each element in it is an Ivar, and then assign to them separately. But as soon as we start dealing with fancier data structures, like map data structures, tries, hash tables, and so on, we start running into situations where we can't fake a solution just with Ivars. So to do this, we need something more powerful. And so this is the point where I want to turn back to the no shared state idea that I was talking about a second ago, and see if we can draw inspiration from it. And our goal is going to be to see if we can come back to this and generalize our single assignment setting to be able to do things like this. Okay, so KPNs, you're going to be familiar with this if you saw my talk back in March, but I'll just go over it really quick again. So this is one of the classic models of deterministic parallel computation, and these date back to a paper by Gilles Kahn in 1974. And they're sometimes also called Kahn-McQueen networks, after the work he did with Dave McQueen. And they're very simple. So a KPN is just a set of autonomous computing stations that can communicate with each other by sending and receiving data along input and output lines. And those input and output lines are FIFO queues. So we have this group of stations here, C1, C2, C3, and so on. And on its own, each one of these stations has to compute a deterministic function. It has to compute sequentially, actually. But several of them can be running at the same time, so we have parallelism. And the stations are each connected by some input and output lines. So because this one here is the sole input line of C3, I'm going to call that one in C3, and I'm going to call it one output line out C3. So in KPNs, the sequence of data objects that we send along an input line or an output line is called the history of the line. And so, for instance, C1 might decide to send some stuff along in C3. So here we have it sending the number 3. And then a 0, and then a 5. And then C3 might do some computation on those numbers and grind a bit, and then send some values along out C3. So we can write down the history of those lines. And notice the history is always growing. And the way that we'll write it down here, it's always growing to the right. And it's a possibly infinite sequence of values. So the reason I bring up history is that when we're reasoning about determinism in KPNs, we consider each of these stations to be a function from the history of its input lines to the history of its output lines, which was an idea that it took me a little while to wrap my head around. So I want to really dwell on it for a moment. So C3 is really a function from this possibly infinite sequence over here to this possibly infinite sequence over here. And that brings me to the point I really want to make about KPNs and the thing that's crucial to this model being deterministic and even working at all, which is the notion of monotonicity. So what do I mean by monotonicity? So this is something that we all learned about back when we took Calc 1. And we all saw graphs that looked like this, a non-decreasing function with a graph that's going up and to the right with maybe a flat place or two in the middle as an example of a monotonically increasing function. And then something like this going up and down and all over the place as an example of a non-monotonic function. So for the function on the left, for any x and y that we might happen to pick, if x is less than or equal to y, then we know that f of x is guaranteed to be less than or equal to f of y. And that's not the case for the one on the right, where we picked an x that was less than y, but f of x and f of y are the other way around. So more generally, we can say that a monotonic function is one that preserves an order. So we say that a function f is monotonic with respect to an ordering if it's the case that if f is less than or equal to y under that ordering, then f of x is less than or equal to f of y. So to return to KPNs, again, this computing station C3 and its input and output lines, and recall that we'd said that C3 is a function from input histories to output histories. So the question I want to ask now is that function a monotonic function with respect to some partial order on histories? So I'm going to spill the beans and say that yes, it is. And the partial order it's monotonic with respect to is just the prefix of order on histories. So for instance, if you had the history 3, and that's just the history of a line that's just had 3 sent over it and nothing else, is a prefix of the history. Is 3, 0, which is one that's had 3 sent followed by 0. So what would the output of C3 be in each of those cases? Well, it would be 6 in the case of the 3 and 6, 1 in the case of 3, 0. And so running C3 preserved the prefix of ordering. So the function being computed by C3, which is of course the factorial function, is in fact a monotonic function. And this turns out to be not just some nice property, but it's actually crucial for determinism. And KPNs require that the functions computed by their computing stations be monotonic. So I want to make 2 points about what we get from monotonicity. One is that the thing I really want you to be convinced of is that it's monotonicity that makes parallelism possible in KPNs. And none of these computing stations can start doing anything until data reaches them, right? So what we don't want is for C1 to produce all the numbers it's going to produce, and then for C3 to go through and operate on all of them in a batch, and then finally for C5 to do its job. Rather, what we want is for it to be pipelined. So if C1 produces numbers, C3 takes factorial, and and then C5 does something on them, then it's the fact that that prefix of property holds that makes this pipelining possible. And so the second thing that I want to convince you of is that monotonicity causes determinism. So to see that, just consider for a moment what would happen if C3 computed a non-monotonic function. Say, for instance, it computed the parity of the input history length. So the moment C3 is scheduled to run, let's say it looks at its inputs, and it's just received the 3 so far, let's say. So it's received one thing, and and 1 is an odd number, so parity 1. And so it sends a 1 over its output line, and then C5 sees a 1. But then on some other day, let's say the scheduler waits a little longer to schedule C3, or maybe the network latency is lower or something, and C3 runs, it's already received a 3 and a 1, so it's received 2 things, parity 0, so C5 gets a 0. So C5 is observing different outputs depending on what the scheduler felt like doing. And that's an example of what we want to prevent. So that would not be allowed in a KPN. So if there's one point you take away from this talk, it's that monotonicity causes deterministic parallelism. And armed with this idea, let's go back to looking at single assignment languages again, and let's see if thinking about this gets us anywhere. So let's consider what happens in this program. And this is just a not particularly interesting single assignment program. just for the sake of example. So as this program runs, we have a store, and the store grows. And we store a new location value pair for every put that we do. So we happen to be storing 4 in location L1 and in 3 in L2. And then the next 2 could happen in any order. I just happened to pick an arbitrary order here. I could have gone the other way around. So it looks like the store is growing monotonically as the program goes along. And in fact it is. So recall that a function has to be monotonic with respect to a particular partial order. And in this case, the partial order is just a subset inclusion of the store. So let's say the function operating on the store is this function that puts 3 in the location L4. And so again, we're using red for the state of things before the function runs and blue for the state of things after. So checking to see if that inclusion relation is monotonic, this implication holds. So basically what this tells us is that when we write L4, it doesn't matter if L3 was already there or not. We're going to end up okay either way. So we have monotonicity. So here's where we are. We've seen that this notion of monotonicity turns up here, and we've seen that it turned up in KPNs, in these 2 fairly radically different deterministic parallel systems. And here's my claim. Sometimes this notion of monotonicity that we have in single assignment languages is too heavy-handed a notion of monotonicity. It doesn't admit any subtlety, because it doesn't give us any way to talk about the relatedness of stores based on the values that are in the stores. It's blind to that. All it cares about is set inclusion. But it is monotonic, and we know that monotonicity is good. So what we want to do is come up with a subtler way of defining monotonicity than this, that still preserves determinism. So that's what we'll do next. So I was just defining this partial order on stores according to set inclusion. And that means that if you have 2 stores, S and S prime, and you want to know if S is less than or equal to S prime, then, well, you just check that the domain of S, or the names of the locations stored in it, is a subset of the domain of S prime. That's one thing. And then furthermore, that for each location L in the domain of S, S of L is equal to S prime of L. Well, we're only going to change one thing about this definition, as it's written. But it's going to make a big impact. What we're going to do is change the equals sign. We're going to say that if you have 2 stores, S and S prime, and just like before, if the domain of S is a subset or equal to the domain of S prime, and for all the locations in the domain of S, if each of those locations is less than or equal to that value, the value of that location in S prime according to some user-specified partial order, then S is less than or equal to S prime. So it's this user-specified partial order that's going to be the linchpin of what we're doing here. So what does this user-specified partial order look like? So let's go back to our example one more time. So in a single assignment model, you can only write to variables once. But there are no restrictions on the kind of reads that you can do. So what we're going to do is tweak the knobs differently and say, okay, we're going to let you do some kind of multiple writes, but we'll be willing to accept a restriction on reads in return. So this is our example program, but I've made just a tiny one-character change to it, which is that I've added a second argument to the call to get, and that's the number 4. And when we do this, we change the semantics of get as follows. We say that that extra argument being passed is a minimum value that we're interested in reading out of the location. In other words, we want to know if the value has reached a certain threshold. And if it's reached the threshold or crossed it, then we get to read out of the location. And if not, then the get blocks until we do. So doing this, it turns out, is enough to make this program deterministic. Because sooner or later, as the program runs, the scheduler is going to get around to running both branches of this let par, and then eventually B is going to be 4. And furthermore, if we had decided we were going to put 5 here instead of 4, well then the get would just block forever. And so the program would be deterministic because it would always block forever. Yes?
So what if there was a put 4 and a put 5?
So that's what I'm about to get to.
Okay.
So it's not quite that easy, as Jeremiah just pointed out, because even though we made that program deterministic, we haven't done all we need to do. So here's an example of a program that still doesn't work. So this time we have a let par that has 3 parallel subcomputations. And, well, of course, the problem here that we have competing puts. And we're going to be right back where we started, because this program here could evaluate to either 4 or 5. So the final change that we have to make is another change to the semantics of get. And what we're just going to do is say that when we evaluate a get, if the threshold value has been reached, then we return that threshold value. And otherwise we block until we do. So this restriction isn't quite as bad as it might seem at first glance. And we'll see in a minute that it's actually possible to specify a set of threshold values instead of just one value. And there's one other important thing that I haven't pointed out yet, and which is that we're allowing multiple writes, but we don't want to just allow arbitrary multiple writes. Rather, they have to be monotonically increasing writes. And that's where that user-specified partial order comes in. So the way that we enforce this is by changing the semantics of put slightly. So we just say that if somebody tries to do a put to a location that's less than the current value of the location, then the location just stays unchanged. And in fact, what actually happens is that we take the least upper bound of the 2 values that we're putting. But if there's an ordering on them, then of course that just means that we keep the larger one. So in the case of these 2 programs, the user-specified partial order might just be the usual less than or equal to ordering on natural numbers. But they could be various things. Let's say that it's that. But it means that regardless of the order that these puts happen in, whether we put 5 and then 4, or whether we put 4 and then 5, we're going to wind up with 5 in the location. And then the value that we've given as the threshold is 4, so the get will block until the value has reached either 4 or 5, and then it'll unblock and return 4. So what we've done is generalize from single writes to monotonically increasing writes with respect to a user-specified partial order. And when we combine those monotonically increasing writes with threshold reads, we can keep parallelism, or rather we can keep determinism. So the formula that we've come up with is that monotonically increasing writes plus threshold reads equals deterministic parallelism. So if you only take 2 things away from this talk, this is the second thing that I want you to take. So what we have here are just a couple of example partial orders that we might parameterize our language by. Yep, Cameron?
Well, I wanted to ask, what happens if they give you a less than function that isn't anti-symmetric? So like A is less than B and B is less than A, strictly? And yet B isn't A?
It's not a partial order.
Well,
yeah, it has to be a partial order.
Yeah, no pre-orders allowed here.
come on, man.
So there's a non-type rule of correctness too, that you only put in partial orders?
Yes, if it's not a partial order, all bets are off.
So do you throw some kind of error in this case? Like, or do you just say, you're shooting yourself in the foot, good luck? The second's an acceptable answer, I'm just wondering.
There is, in our implementation, there is no system that checks to make sure that it is in fact a partial order.
So
But that's an interesting idea. Zach?
I thought about this briefly, and it seems like, at least for a certain class of errors, it just makes everything less than everything else. So it'll just return whenever anything is written in the Ivars, which seems like not the most useful semantics, but also not broken in any obvious way.
Well, but it's not deterministic then, because it'll return an arbitrary value, right, based on the order, you know.
I'm not sure what you mean by everything is less than everything else.
Well, so if you have 2 objects, and they're both less than each other, but they're distinct, then they're all. I'm thinking specifically of like a logic that's unsound, so you can prove bottom.
Okay.
And in that.
So if I hand you something that's just not even a partial order, then it's not going to work.
That's a pre-order.
Okay.
Eric?
I wouldn't be surprised though if you had the case where like you could have like A and B such that like A is less than or equal to B and B is less than or equal to A, but they're not actually equal. That you might still get determinism if you define equality as less than or equal to, like one's less than or equal to the other and the other is less than or equal to.
Okay.
Like,
Yes, you can convert every pre-order into a partial order.
So
in a
this is
canonical
interesting,
way.
because one thing we haven't looked at a lot is like exactly what properties of a partial order we need to we need to have hold, and which parts of determinism would go away in which ways if we eliminated each one of those properties. So that would be something worth looking at. We did look at the notion of whether it had to be a lattice, or as it turns out, it doesn't have to be a lattice, it just has to be a joint semi-lattice. But we didn't think about this quite to the extent that you guys are thinking about it right now. So that's interesting.
But hold on, real quick to answer Zach's question. So the order you were proposing was one in which there's a bottom element and everything is greater than that bottom element, but there's no other relationship?
Or I guess rather there's a bunch of elements, and for all A and B, A is less than or equal to B.
We're also assuming that there's a bottom that's less than everything.
Yeah.
Oh, for all A, okay. But I thought you were creating a situation where there were a bunch of elements, but it looked like this basically, where you have some bottom element and a lot of elements that are unrelated to one another. So I misunderstood your question.
Sure, yeah, I guess that's probably also interesting to think about.
Well, that would turn into, and the answer to the question you didn't ask was that
Okay.
that would turn into basically an Ivars unit, where you could distinguish it was full or not, but you couldn't extract any other information from it.
I guess that is what I meant to ask then. Because that's or rather that's the result that I had in mind.
Sure, okay.
So are threshold reads the only type of read you support?
Yes, yeah.
Seems like it would be very limiting in terms of like getting the answer back out of a computation.
Yeah, so threshold reads do seem really restricted, and that's something that we think that's kind of an interesting thing as well. But that's, as far as we've been able to figure out so far, that's the only way to maintain determinism in the face of monotonic updates.
Why
So.
restriction? You can ask up to any precision you want. Did you reach that precision? Yes or no?
Well, no, because it'll block if you didn't.
So until it will reach it, right? So yeah, it will not.
So the next
picture.
picture that I'm going to show might actually help a little, because I'm going to talk about having threshold sets instead of just single threshold values.
There's also, unless you guys get rid of it, there's another type of read which is basically, at the end of time.
Oh, yeah.
Yeah.
So we also have so-called destructive reads, which let you do what we're calling